This is Chapter 4, Atoms and Elements. Section 6 is Electron Energy Levels. So we remember the structure of the atom, right? Atoms are made up of a very small nucleus that has the neutrons and the protons inside, and so it has a positive charge, and almost all of the mass of the atom is packed into the tiny nucleus at the center. And then around the nucleus, there's a large volume of space, which is mostly empty, but which is where you find the negatively charged electrons. So it's the electrons that determine the physical and chemical properties of an atom, right? For instance, if two atoms come close to one another, it's the outer electrons that are going to start to interact first, and so those are going to determine the reactions that occur between those two atoms. Because the electrons are what determine the chemical and physical properties of an atom, we're going to want to spend a fair amount of time looking at how the electrons in an atom are arranged, because that's going to determine that chemistry. And so we're going to look at what we call the electronic structure of the atom, right? How the electrons are arranged in an atom. So the first thing to know is that electrons in an atom each have energy, right? The electrons are moving and they have some distance relative to the nucleus, so they have both kinetic and potential energy. Low energy electrons are close to the nucleus, high energy electrons are further away. Okay? Just like with gravitational potential, the lower gravitational potential is when you're closer to the ground, and if you add energy, it gets you further away from the ground. That's higher energy. Okay? So it's similar with protons in the nucleus and electrons surrounding it. The next thing about energy levels, which is very different from our everyday experience, is that electron energies are quantized. Okay? What this means is that they only come in certain specific energy levels. Okay? An electron in an atom cannot have any arbitrary energy that you want to give it. It can only exist in certain states that have specific energies. So to understand why this is weird, think about a pendulum, right? You'd have a mass at the end of a string, and if you pull the mass up to one side and let go, then the pendulum swings back and forth. Okay, so in doing that, it has energy, it's transforming potential into kinetic energy and back and forth. But you can pick up the mass to any height and release it from that height. Okay, and the mass, whatever height you released it from, the mass will have a certain amount of potential energy at the beginning, and so that will be the energy level that that mass is in. And you can choose whatever height you want so that the pendulum can have any energy that you want. In an electron, or in an atom, I should say, the electrons, you can't choose any distance from the nucleus. You can't give them any arbitrary energy. So if the electron were like a pendulum, it would be like if you were only able to raise the pendulum mass to certain specific heights. Okay? And you couldn't put them at those other heights in between the selected levels. Okay? So it's a very strange way for things to behave, but this is just how things behave at the atomic level. Okay? So since we have these discrete energy levels, we can label them, right? They do have energies and we can calculate energies for them, but we're not really going to be interested in the actual energy amounts in this class. Instead, we're going to think about these energy levels as being labeled by a number, and we call that number n, or the principal quantum number. But that's a mouthful, so we just call it n. Okay? The lowest energy level, meaning the level that's closest to the nucleus, is n equals 1. Okay? So there's no n equals 0 level. Right? What that means is that the electron has to have some energy. You can't remove all of the energy from an electron. So the electron can never lose all of its energy and crash into the nucleus. Right? That never happens. So the lowest energy level is n equals 1. The next highest energy level, the one that's a little bit further away from the nucleus, is n equals 2, then n equals 3 and 4, etc., and so on and so on. Okay? So electrons that have the same energy are said to be in the same energy level. Okay? And an energy level can only hold a certain number of electrons. One way to think about this is to use the metaphor of, say, a bookshelf. Okay? So a bookshelf, the books on the different shelves in a bookshelf have different energies because they're different heights from the floor. Right? But in an atom, you can only fit a certain number of electrons in an energy level. So it would be like if your bookshelf only had room for a certain amount of books, which it does, but the difference is that the higher you go, the more room you have for books, right? So the bottom shelf, say, could only hold 2 books, and then the next highest shelf could hold 8 books, and then after that, 18 books, and so it would go up like that. Okay, so the lowest energy level, n equals 1 in an atom, can only hold 2 electrons. Okay, higher energy levels will be able to hold more electrons, and there's a way we can count that. Now, keep in mind, when we say an energy level is holding 2 electrons, we're using the language in a way that we're trying to convey sort of a complicated idea. The idea is that these 2 electrons have the same configuration, they have the same arrangement in the atom, and so because they have the same arrangement, the same distance from the nucleus, the same speed, things like that, that means they have the same energy. Okay, so they're not like physical, I mean, they are physical regions of space where you find the electrons or where you're likely to find the electron, but the idea of an energy level holding electrons is sort of a linguistic metaphor. Now, because electrons can only occupy certain specific energy levels, if we want to move an electron from one energy level to another, in other words, if we want to somehow rearrange the electron or give it a different configuration in the atom with a different energy, we have to provide energy to do that, to move it up, right, to give it more energy to bring it to a higher level, but it has to be a specific amount of energy. The amount of energy we give it has to be exactly equal to the difference between the 2 energy levels. Okay, so if you're going from a lower energy level to a higher energy level, you have to put that energy in. Okay, and the way this typically happens in an atom is that the electron will spontaneously absorb energy. It'll absorb a photon of light, for instance, or it can even just absorb heat from the surrounding environment. And so if it absorbs energy that's exactly equal to the distance between the 2 energy levels, then it can bump up and it can go up to the higher energy level. Okay? And once it's there in the higher energy level, it's going to be a little bit unstable. Okay, because there's room for it to fall back down, for it to lose energy to go back down. And so it can do that. It'll go back down to the lower energy level by releasing that energy as usually as a photon of light of a specific frequency or wavelength. Okay? So the energy emitted or absorbed is equal to the energy difference between the 2 levels, right? It's absorbed if it goes from a lower level to a higher level, and it's emitted if it goes from a higher level to a lower level. So if you have a larger difference between the 2 energy levels, like you see here in the bottom picture, right, it's a larger gap between the energy levels, then it requires a larger amount of energy input. Okay? And when it falls back down, it's going to emit, it's still going to emit a single photon, but that single photon is going to be higher in energy. And the way that a photon is higher in energy is it has a shorter wavelength. And so we see that here. Okay? Within any given energy level, there are several sublevels. Okay, so remember again that an energy level is a particular arrangement of electrons in an atom. So what the sublevels are slightly different ways of arranging the electron that still end up with the same overall energy. Okay, so the electrons can be grouped into these different sublevels for each energy level. And for each energy level, the number of sublevels, the number of different ways that you can arrange the electron to have the same energy, is equal to n, the principal quantum number, right? The number that we've given to label that energy level. Okay? And then the labels that we have for the sublevels are S, P, D, and F. Okay? These seem a little bit arbitrary. They have some archaic significance in terms of spectroscopy and the early study of atoms. At this point, that etymology is pretty much lost, so all you need to remember is that the sublevels are S, P, D, F. And then if we get higher energy levels, we can have more sublevels, but after F, they just go alphabetically, so it'll be F, G, H. You're never going to get that high because S, P, D, and F energy levels account for pretty much all of the elements in the periodic table. We'll see what I mean by that in a little bit. And this is the order of the sublevels as well. Okay, so the order is that the S is a little bit lower in energy than the P, which is a little bit lower than the D, which is a little bit lower than the F. Okay, so even though all of the sublevels within an energy level give approximately the same energy, and that's why they're all considered part of the same energy level, there is still a little bit of a difference, and so there is still an order to the sublevels within an energy level. And now we can also subdivide the sublevels. So the sublevels themselves can be broken up into what we call orbitals. Okay? And so an orbital is really a specific shape or a specific region of space around the nucleus where you're likely to find an electron. Okay, so the electrons exist in these specific arrangements, which are really orbitals, and we can think of different orbitals as being identical to one another, and identical orbitals constitute a sublevel, and then sublevels that are similar enough in energy can be grouped together, and that constitutes the overall energy level. Okay, so it's sort of a hierarchy. It breaks down from the energy level to the sublevel to the orbitals. Okay, each orbital holds 2 electrons at most. Okay, they can have only 1 electron, or an orbital may have no electrons if they're not around with enough energy to get into them. But at most, an orbital can hold 2 electrons. Okay, there are a certain number of orbitals depending on the sublevel type. So just like each energy level has a certain number of sublevels, each sublevel has a certain number of orbitals, and it's based on what type it is. Okay, so you have the S sublevel, which is 1 orbital. The P sublevel is always 3 identical orbitals. The D sublevel is 5 identical orbitals, and the F sublevel is 7 identical orbitals. Okay. Here we have these energy levels and sublevels and orbitals drawn out a little bit more clearly in the form of a diagram. Okay, so we have the energy levels increasing from the bottom up. So we have n equals 1 on the bottom, and n equals 2, n equals 3, n equals 4. So the idea is as you get a higher n number, you have a higher energy, and so it goes up. Right? It's easier to think about it that way. Lower energies are at the bottom, higher energies are at the top. And so we can see the sublevels, the number of sublevels here, and then which sublevels they are listed here with the number of orbitals in them. Okay, so the individual boxes, the colored boxes here on the right-hand side, are orbitals, and they're grouped together into sublevels, which are then grouped together into the energy levels, which are the rows. Okay, so the number of sublevels, remember, is always the same as the n value. So for n equals 1, you just have 1 sublevel. And for each sublevel, you always start with S, and then P, and then D, and then F. So if there's only 1 sublevel in an energy level, it must be an S sublevel. Okay, so this is n equals 1, and it's sublevel S. So we can think of it as a 1s sublevel. Okay, and this box is the orbital, because an S sublevel is always 1 single orbital. So it's 1 box. Okay. For n equals 2, we have 2 sublevels. Okay, and you always, again, start at the S, so you have an S sublevel for n equals 2, and then you have a P sublevel for n equals 2. The S sublevel is always a single orbital, it's an S orbital, and so we have n equals 2, and then the sublevel is S. Okay, for here we have n equals 2, and the sublevel is P, so we can think of it as a 2P sublevel. We write it that way sometimes. And the P sublevel is split into 3 distinct boxes. Okay, in this case, 3 orbitals that are basically the same. They have the same energy, but they're a little bit different in terms of their orientation. Okay. For n equals 3, we have 3 sublevels. We have an S, we have a P, and now, since we need a 3rd sublevel, we also have a D sublevel. Okay. So the S sublevel for n equals 3 is a 3s orbital. It's a single 3s orbital. For the P sublevel for n equals 3, the sublevel we can call 3p, and we would say that there are 3 separate 3p orbitals, okay? Because every P sublevel is split up into 3 orbitals. Every D sublevel is split up into 5 orbitals. And so we could say that the sublevel is 3d, right? And we could also say that there are 5 of these 3d orbitals within the sublevel. And then for n equals 4, you have 4 sublevels, so you finally get to the F sublevel, right? And the F sublevel is always split up into 7 orbitals. So you have 7 4f orbitals, okay? You have 5 of the 4d orbitals, you have 3 of the 4p orbitals, and you have a single 4s orbital, okay? So for each energy level, you have an increasing number of sublevels, and for each sublevel in order, you're increasing the number of actual orbitals that you get. Okay? So a sublevel can be represented by the energy level that it belongs to, followed by the sublevel type, right? That's what I was writing here with these lines. So 3D refers to the n equals 3 energy level and the D sublevel. This chart summarizes some of the information from the previous slides in terms of the total number of electrons that can fit into each energy level or sublevel or orbital. Okay, so for instance, the n equals 1 energy level is here, right? And since it's n equals 1, it has only one sublevel, which must be an s sublevel. An s sublevel is always a single orbital, which means it can hold only 2 electrons. And since that's it for this energy level, then the total number of electrons in the n equals 1 energy level is 2. Okay? But to give another example, for n equals 3, you have 3 sublevels, right? And the 3 sublevels are s, p, and d, 1, 2, and 3. S orbitals, there's always one s orbital by itself, there's always 3 p orbitals together, and there's always 5 d orbitals together. So in the s sublevel, you can fit 2 electrons. In the p sublevel, you can fit 3 times 2 electrons, or 6 electrons. And in the 5 d orbitals, you can fit 5 times 2, or 10 electrons. And then if you add all of these up, you get 18 total electrons in the n equals 3 energy level. So taking a closer look at the s orbitals, like I said, the orbitals are specific physical or spatial arrangements. They're spatial regions where you're likely to find the electron. So for the s orbitals, all of the s orbitals are spheres. They're spherically symmetric, centered around the nucleus. Okay? So every energy level begins with at least an s sublevel. Okay? And every s orbital is a sphere. As you go up in the energy levels, the spheres get larger, because as you get higher in energy, you're getting further away from the nucleus. So the 2s electrons are in a sphere, but they're in a sphere that's further away from the nucleus than the 1s electrons. They have a larger diameter, larger radius. Okay? So again, each orbital can hold a maximum of 2 electrons. So the s sublevel for any given energy level, the s sublevel can only hold 2 electrons because it's only a single orbital. Starting at the second energy level, n equals 2, you now have a new sublevel, right? Because n equals 2, so beginning there, you have to have a second sublevel, and it's going to be a p sublevel. The p sublevel is always 3 orbitals, okay? They have this strange shape, which we'll see on the next slide, and they all have the same exact shape, but like I said, they all have different orientations. So for the p orbitals, they're all perpendicular to one another, and so you can think of them as being like the x, y, and z axes in a graph. Okay? And a p orbital can also only hold 2 electrons, because any type of orbital, regardless of sublevel or energy level, a single orbital can only hold up to 2 electrons. But because there are 3 orbitals in the p sublevel in total can hold up to 6 electrons. Okay? Now keep in mind, this is beginning at n equals 2, because this is the first time when you get a second sublevel. In the n equals 1 energy level, there is no 1p sublevel. There's only a 1s. Okay? So there's no such thing as a 1p sublevel. This is what the orbitals look like, the p orbitals. On the left are these 3 pictures. Okay? They have this sort of dumbbell shape with their lobes sticking out from the nucleus. And on the right, you see an image of all 3 of them superimposed over one another. Okay? So this is not a separate orbital itself. These are the 3 p orbitals here. Okay? And just like with the s orbitals, p orbitals in higher energy levels are larger. Okay? So if this is the 2p energy level, well, the 3p energy level, or the 3p orbitals, will have a similar dumbbell shape. They'll be pinched at the center, but they'll have bigger lobes. Right? The lobes will be further away. Okay? This would be bigger. So anytime you're going to a higher energy level, the electrons are getting further away. D orbitals are even more complicated, right? So these all have similar energies, or really identical energies, but they're not just simple rotations, although some of them are, but then you also have like weird ones like this. So we're not really going to worry about where these shapes come from or the orientations or anything, but you should know that D orbital, first of all, begins at n equals 3, so there's no 2D orbital, right? And there's no 1D orbital, okay? That's what it says down here. No 1D or 2D sublevels. But beginning at n equals 3, you have a D sublevel, and a D sublevel is always 5 orbitals. Each orbital can hold 2 electrons, so the D sublevel can hold a maximum of 10, right? 2 electrons per orbital times 5 orbitals gives you 10 total electrons in a D sublevel. And again, the size increases as the energy level gets higher. Let's take a look at an example of a type of question you might be asked about this. Okay? So this question says, indicate the type and number of orbitals in each of the following energy levels or sublevels. So it's going to either specify a whole energy level, or it's just going to tell us an individual sublevel. Okay? And it wants to know the number of orbitals for each. To analyze the problem, you know that you were given a certain energy level or a specific sublevel within an energy level, and you need the number of orbitals, but really the only connection that you can make between the two is to just remember the rules that we were presented on the previous slides. You need to know how many sublevels are in an energy level and how many orbitals are in a particular sublevel type, the sublevel types being the S, P, D, or F letters. So step one would be to identify the principal energy level, the N value. Okay, if you're given the N value, if they tell you N equals 1, then it's given. N equals 1, that's the principal energy level. Okay, N equals 4, that's the principal energy level. It's just given to you. If you're given a sublevel like this, then you have to look at this symbol and say, well, the number here is the N value. Okay, so if you're given a sublevel in terms of like a 1s or 2p or 3d, the number in front is the N value. So in this case, N equals 3. And then you have to identify the sublevels. Okay, so for the entire N equals 1 energy level, because N equals 1, there's only one sublevel, right? The number of sublevels equals the N value. For this one, we know that for N equals 3, there should be 3 sublevels. However, this is specifying the P sublevel. So now we only need to worry about those orbitals within the P sublevel of N equals 1. For N equals 4, again, because the number of sublevels equals the N value, we now have to worry about 4 sublevels. Okay? And so the 4 sublevels, remember it always starts at S and proceeds from there, so we have S, P, D, and F. Those are the 4 sublevels. Now that we know the energy level and the sublevels that we're looking at, we need to just remember the rules that tell us how many orbitals constitute that sublevel. Okay? So for instance, in any S sublevel, whether it's 1s, 2s, 3s, or whatever, any S sublevel is only a single orbital. Okay, so in this case we have one orbital and it's designated as a 1s. That's the type. For 3p, we're talking about a specific sublevel, remember, and it's a p sublevel, and p sublevels, the rule is, are always 3 orbitals together. So in the 3p sublevel, we have 3 separate orbitals, but they're each considered a 3p orbital. For n equals 4, we have a lot more, right? We have 4 different sublevels. We have 4s, 4p, 4d, and 4f. And again, just remembering the rules, an S sublevel is always 1 orbital, a p sublevel is always 3 orbitals, and a d sublevel is always 5, and an f sublevel is always 7 orbitals. So to answer this question, right, it says indicate the type and number of orbitals in each of the following energy levels or sublevels. So in the entire n equals 4 energy level, you have a single 4s orbital, you have a set of 3 4p orbitals, you have a set of 5 4d orbitals, and you have a set of 7 4f orbitals.